Part D. Philip rubs his hand against his leg. Explain, in terms of energy transfer, how this results in his hand warming up. Well, we need to start with energy transfers right from the source. The source of energy inside Philip's body is the chemical energy from his food that he has consumed. So chemical energy in his body is converted to kinetic energy, which makes his hand move. And this then is converted to heat energy due to friction. So there are 3 marks therefore. What do we get the mark? The first one is for relating it initially from the chemical energy, then the conversion to the kinetic energy gets you the 2nd mark, and the 3rd then mark comes then from the heat energy due to friction. Now, part 2 of this question. This second part of part D relates to movement of forces and distance. Therefore, it's more closely linked to Unit 10, but for the sake of completeness, we will do this calculation here. So the average force Philip uses in rubbing his hand against his leg is 10 Newton. His hand moves a total distance of 20 centimetres. How many such movements does he have to make before he supplies 50 joules of heat to his hand? You're advised to show clearly how you get your answer. Now, there's 5 marks for this, so there are several stages to the calculation. And the more clearly you lay out your calculation, the more sure you are of getting all 5 marks. Even if you make a mistake during your calculation, it will be a whole lot easier to pick up marks for your method if you show it clearly. First off, the distance is 20 centimetres. The first thing we notice is that that's in centimetres, which isn't the standard unit, so we must convert that. So 20 centimetres equals 0.2 metres. And that's the first thing you should do, is recognise the fact that that's in the wrong unit. The next thing is then to work out the work done for one movement. And the equation for that is work equals force times distance. So for one movement, and I would clearly just write down, show clearly exactly what you're calculating. For one movement, the force of 10 newtons is moved by a distance of 0.2 metres. So for one movement, uses 2 joules of energy. Now, the next part of the question. How many movements does he have to make before he supplies 50 joules of heat to his hand? So we want 50 joules, and it's 2 joules per movement, so it needs 25 movements. And remember to write it down in the space allocated to it. Now, where did the 5 marks come from then? Well, it's surprising how many marks you can get, even you don't fully get through the question. You would get a mark for converting the centimetres to metres, and a 2nd mark for writing down the equation. A 3rd mark for calculating the energy of one movement. 4th mark then for working out that to get 50 joules of energy, and it's 2 joules per movement, showing that calculation gets you a 4th mark. And the 5th mark then comes from working out that it's 25 movements. So even if you look at that question and you really don't know where to start, if you think about work done and write down that equation, it gets you a mark. If you think, well, centimetres isn't useful, that gets you a mark. And once you've written those 2 things down, it may start to lead you into the calculation properly. And remember, every mark counts. It could be that 1 mark that makes the difference from one grade to the next. Continuing that question then. What further information would be needed to calculate the average power developed in this process? Well, if you remember your equation for power is energy over time. We've worked out energy, and to get to power, the measurement we need is time. Or you could write this down as the duration of hand rubbing. So we need a measurement of time. Write down the equation you would use to calculate the average power using the extra information. You could write it as power equals energy over time, or you could do it in words. Power equals energy over time, or even work done over time taken. Any of these is acceptable. The final part of this question relates to electricity generators and the resources used for those. Electricity generators can use many different energy sources. The following table is intended to give some of the advantages and some of the limitations, and the table is incomplete. Please complete the table. The first line has been completed for you. An oil-fired power station has a very large maximum power output. Its speed of response to changing demand is slow. The reliability, you can have uninterrupted supply, and can be suitable for standby for hospitals. Yes, it can be because the supply is uninterrupted. Now, a nuclear power station, it has a very large power output. The speed of response to changing demand, again, it's slow, and is in fact even slower than the oil-fired power station. The reliability, again, you could copy in the same idea, uninterrupted supply. And is it suitable for standby for hospitals? Yes, it is, because of that nature of the uninterrupted supply. However, you could have mentioned some concerns about the reliability in terms of the safety of the personnel working with it, or the risk of danger to health due to the reactivity of the nuclear material, and in that case then you could possibly say that it's not suitable for standby for hospitals. But there must be a flow of logic there in terms of, if you said it was reliable due to its uninterrupted supply, then yes, it's suitable for standby for hospitals. Poorly worded question, to be honest. A single wind generator, it has small or very low maximum power output per generator. The speed of response to changing demand is quick. The reliability, it's very unpredictable and unreliable, because basically you're relying on the wind, which is out of your control, so it's unpredictable. And due to that, it is not suitable for standby for hospitals.